Now we discuss another example. So say you have a data process. So you have given data, we are going to generate this data and then use it. So this data, it has a trend and it has a autoregressive process. So for example, say the data is generated by some underlying process like this: yt is equal to 10 plus 0.5 times t plus 0.9 yt minus 1 plus this error term. So this is the time series part. So this is the time series part, and this is the trend part. So what we are going to do is we are going to simulate 100 data points from this series. So we are going to simulate the above series and store 100 data points in the series, and then we are going to put some model on these data points. So instead of these 100 data points, you could just choose the prices of your favorite commodity. So you could place your own data in the set of 100 points. I'm using this model because then once the results come out after fitting the model, we know how to compare those results with the underlying process. And you can place your own 100 points. Instead of my 100 points, you could place your 100 points and call the series as data. So for example, this could be your price of favorite commodity. So the simulation is done by, this is the time series simulation part. So simulation is done in two parts. So the first part is this. So this part is done right here. So you have 100 data points coming for this time series part from here. So this is 0.9 comes here. Then I have to simulate this trend part. So for the trend part, 100 data points, the time is 1 to 100. So time is 1 to 100, and finally the data set would be 10 plus 0.5 times time. So this is our data part plus y, where y is our this time series part. So this is 100 data points now. This y is the time series part, this is the time series part, and this is the trend part. So this is the time series part and this is the trend part, 10 plus 0.5 t. So here time is series. R is smart enough to extend 10 to all 100 vectors. So the first step is to plot the data. So we want to plot the data and see. So this data I have generated like this, but instead of this 100 points, you could have your own 100 data points. So now imagine that you have your own 100 data points. So I'm using my 100 data points generated from this process. You could put in your own 100 data points. So now we will plot this data, and we already know that there is no seasonality of data. So before you put in your data, you should be clear in your mind that there is no seasonality. So because we are not using seasonality in this process. So this could be, say for example, demand for copper. You can say there is no seasonality for demand of copper or demand of aluminum or demand of iron, something like that. So the first step is you need to plot your data and see what it looks like. So now when you're going to plot your data, you do not know if there is a trend in the data or not before you plot it. So I have generated data which has a trend, but you could have data about which you do not know. So let us just plot what I have and see what it looks like. So you copy paste this from the description of the video. So we first have to run these 3 lines so that you have the data. Now you have the data. Now we just plot this data. So you plot the data, this is what you get. So you see this data just looks like some prices of some commodity which is increasing over time, and you can see there is a trend line to it. So if there is a trend line to it, we cannot fit time series directly. We have to remove this trend line. So let us go back and try to remove this. So we just saw by plotting data that there was a trend. And to fit time series, you cannot fit it with trend. You have to remove this trend because this trend is regression part. So you construct the first model. So the first model is nothing but a linear model. So this will take this data and fit it to time. So this is the model which will come out, and then we will check the confidence interval of the model. So once you have the confidence interval, then it will tell you if time is actually significant. Time is significant or not. So my underlying data process already has 0.5 in it. So when you want to simulate it, you will find M1 coefficients. You want to see this 0.5. And after we have built the data this we have fitted the model, then time series will be fitted to residuals. So residuals means that you will take the trend part out in this model M1. So the model data to time is exactly fitting this model. Data to time means it will give you something like a constant plus alpha times time. So you will find the constant and find alpha, and we will find out the result. So we are back to our model. So model is fitting data to time, and this is the model one. So let us run all three of these commands together to see what we get. So you get the intercept as 11 and time as 0.48, and both the time has confidence interval from 0.7447 to 49. So this does not have 0, so time is significant. Intercept is from 10.5 to 11.6. It does not have 0, so this is significant. So let us record what the model we got. So this is the model we fitted. So we started with this model 10 plus alpha t, where alpha was 0.5. So this is the model we started with. But when you fit it, this constant comes out to be 11 and this alpha comes out to be 0.48. So notice that this 11 and 0.48 are different from 10 and 0.5, the process we generated. But they're not that different because 11 and 10 both lie in the. So notice that this intercept is 11.07. So is it different from 10? Mathematically, yes. But it is very close to 10 here in the confidence interval. So 10 lies slightly below here, but still it is close. Again, this is all because of the noise in the process. Similarly, 0.48, ideally both 0.48 and 5 should lie in the interval, but because of some random errors which we have added, these are different. So the idea is this: you could feed in your data set and find out your values. So for once you feed in values, what you get is completely different from what you started with, and that is precisely because you are introducing this error term. This error term is the one which is causing the problem, getting you 11 and 0.48. And in fact, we see that 11 and 10 are not in the same confidence interval, so they are kind of different now because of the error, but you're still close. Now the idea is the time series is fitted on residuals, so you have to take the time out. So that is, you take out the trend. So you take this trend out and you fit time series on the residuals. So let us do that. So now we are here. So you name time 1 as the residuals, and then you fit the partial autocorrelation function on time 1 and autocorrelation function on time 1. And let us do that. So this is the autocorrelation function which comes out, and let me run the partial autocorrelation function, and this should just show us one lag. So let us run this. So this is what we get as a partial autocorrelation function. So you see there is exactly one lag. Every other residual is within the blue lines, that is the not significant. So between the blue lines means these residuals are not significant. So the partial autocorrelation function, which you can read here, partial autocorrelation function, exactly shows there is one lag. So we should be fitting in one lag model. So let us do that. So the model we are going to fit is y of t is alpha y t minus 1 plus a constant plus epsilon t. So this is the model we are going to fit, and that is precisely the model right here. ARIMA time 1. Time 1 is what the data set you are fitting in. Order is 1 0 0. There is no moving average, only one lag. So we will run the model. We will check the residues. We do a Shapiro test in residues, and we have to make sure that these residues are normally distributed. So we want Shapiro test's value to be greater than 0.05, so that you do not reject the null hypothesis. And then we will check out the confidence intervals and see what comes out. So let us run the model. You select this, hit the run button, So we have run the model. Now let us do the residuals. Let us do the Shapiro test on the residuals. Shapiro test gives us p-value of 0.9335. It is greater than 0.05. You say, okay, the errors are fine, they are normally distributed. Now let us do the run the model. So the model gives intercept as minus 0.02 and first as 0.76. This AR1 is 0.76. So now what we do is you check the confidence intervals. So AR1 confidence intervals goes from 0.63 to 0.88. It does not have 0 in it, so what we have found is significant, and the intercept contains 0. So the intercept is insignificant. So this minus 0.209, this is actually statistically equal to 0 because both minus 0.02 and 0 lie in the confidence interval, whereas this value of 0.76 is what we want. Now notice that this 0.76 is actually not, so we have found the model, this 0.76 is not actually 0.9, and in fact 0.9 does not even lie in this interval, and that is interesting to see because when we started the data process we did put in 0.9. So let us summarize what we have. So we have found that this alpha is something like 0.74 and this constant is 0, and that is the story. That is what we have found out. And then you can do prediction. The prediction comes in two parts. Obviously first part is you predict your linear model. So this is predicting a linear model. So you predict your linear model, and I'm doing it 10 steps ahead, so 10 ahead. Then you predict your M2. M2 is your time series model. So this is your time series. So then M2 is your time series model. You predict that. And so P2 $predict will give you 10 values for M2, and then you can run P1 plus P2 to find the 10 values for prediction. So again, this is machine learning. The predicted values coming to your machine learning. But again, these values just give you an average value. This is the expected value of the random variable. But when you actually find the values, they will lie very close to your predicted values, but not exactly your predicted values. So it is almost impossible to predict the values exactly in the future. What you can predict is that the values in the future are going to be close. They are going to be around this prediction. So therefore we need to give specific meaning to the word around, and this around essentially means that we need to simulate it and fix some probability distribution function on it, so that you know how much around they will be, what is the probability that they are going to be around this and away from this, so that then you can use these time series to buy or sell call options. Because then you can see, you know, if other person does not know probability, then you can use your time series to understand that if he's selling a call option which is worth buying or not. So let us just run these predict commands once an hour, and then we are done with this lecture. So this P1 is you predict the linear regression. P2 is you predict the time series. Now let us just see P1. So P1 is these 10 values. These are all coming from the trend. These are the values of the trend P1. P2 is P2 $predict means that values of P2. So this is a time series. It shows time series start at 101 and at 110. So these are the values from time series. So time series is predicting negative values for you. Then this is your total prediction. So this is your total prediction, which is both the trend and the time series. As said before, the prediction does not mean anything. You expect the values in the future to lie around these values. It is impossible that what you predict will be exactly the future, but the future values you expect to lie around these values, and that needs to be properly said in terms of probability.